Okay, Bismillahirrahmanirrahim. Just to recall back on what we did yesterday, we looked at the substitution reaction of halogenoalkanes with cyanide ions and with ammonia. The one with the cyanide ions, it's pretty standard because it's similar to the reaction with hydroxide ions. With ammonia, however, it's a little bit different because ammonia is a neutral nucleophile. So what happens is that when the lone pair on the neutral ammonia molecule is being donated to the carbocation or being donated to the halogenoalkanes, the nitrogen will now form 4 bonds. And because it has given away its lone pair, the nitrogen will develop a positive charge. In order to remove that positive charge, one of the nitrogen-hydrogen bonds must be broken. And the lone pair, the pair of electrons from this bond will be donated to the nitrogen, and the nitrogen will restore or will get back its lone pair. So this being said, excuse me, the lone pair on the product, which is an amine in this case, can act as a nucleophile and attack a molecule of halogenoalkanes. So this is the reason why we want ammonia to be in excess, because ammonia and amine can act as nucleophile, but if we have ammonia in excess, amine will have to compete. And because amines are present in small amount, it wouldn't be able to attack halogenoalkanes as much as ammonia. Okay, the next reaction that we're going to look at is the reaction with aqueous silver nitrate in ethanol. So that means, sorry. Okay, I'm back. So the next learning objective that we are going to look at is the reaction with aqueous silver nitrate in ethanol. So this method is also a method to identify the halogen presence. I'll explain to you why that's the case. Okay. So first, aqueous silver nitrate, there are actually 2 types of reactions happening here. The first one is the substitution with water. The second one is called the precipitation reaction, which we will look at later on, right? So the first reaction is called a hydrolysis reaction, and hydrolysis reaction usually involves water molecule to break down the carbon halogen bonds. Okay, so please add this into your notes, where this reaction is called the hydrolysis reaction. It is a reaction that involves breakdown of substance by water. Hydro is water and lysis means broken down. Okay. Right. The condition for this reaction is quite standard. You heat it under reflux. So I'll just draw out what happens. We have, if we take an iodoethane, and then we react it with water, H2O. Water comes from the aqueous part of silver nitrate. Sometimes it's not that obvious. Whenever students look at the question, it says silver nitrate aqueous, they start to think, oh, silver is acting as a nucleophile, or nitrate is acting as a nucleophile, but actually it's just the aqueous bit. The water in the silver nitrate is acting as a nucleophile. That's why if you notice with potassium cyanide and with sodium hydroxide, we use ethanol as the solvent. We don't use water because water acts as a nucleophile as well. So if you use aqueous potassium cyanide, there will be a competition between the cyanide ions and also with the water molecules, because both of them are nucleophiles, and you will get a mixture of products. Okay, so what happens when water hydrolyze your halogenoalkanes? You will form a new functional group called the alcohol. So this is similar to the reaction with ammonia. In your water molecules, there are 2 OH bonds. However, in your products, there is only 1 OH bond. Okay, because if you have 2 OH bonds, that means your oxygen is bonded to 3 atoms, and oxygen is usually bonded to 2. Maximum number of bonds that it can form is 2. Okay, so your hydrogen must have been lost somewhere, which I will show later on in the mechanism. Okay, and the other products would be H+, which was from your water, and iodide ion, which was from your halogenoalkane. So during this hydrolysis process, it is just like all the other substitution reaction, the carbon halogen bond breaks, okay? And the other products are H+ and I-. So this reaction is similar to the nucleophilic substitution reaction of halogenoalkanes with aqueous alkali. This was the very first reaction that we saw, the reaction of hydroxide ion as your nucleophile, and the source would be sodium hydroxide or potassium hydroxide, okay? But the only difference is that the reaction with hydroxide ion is faster compared to the reaction with water. Both of them will give you the same products, which is an alcohol. Okay, so this means that hydroxide is a better nucleophile, or is a stronger nucleophile compared to water. So what is the reason for this? The reason is because of the charge. Hydroxide has a full negative charge, so it is more reactive. It is more, it's stronger as a nucleophile. Compared to water, there's a lone pair on the oxygen. The charges are only partial, delta plus, delta minus. Okay, so they are not as good as hydroxide as a nucleophile, right? So please copy this down in your notes. Just below where it says the hydroxide ion is a better nucleophile than water, as it carries a full formal negative charge, whereas in water, the oxygen atom only carries a partial negative charge, delta minus. Okay, so this causes the nucleophilic substitution reaction with water to be much slower than with aqueous alkali. Okay. Yes, thank you, Lim. I got the text from Daniel as well. Right, in the next slide, I will show you the mechanism for the reaction of halogenoalkanes with water, both Sn1 and Sn2. Okay, so the water molecules is actually coming from the silver nitrate, the aqua silver nitrate, where it will replace the halogen just like how your other nucleophiles replace the halogens in halogenoalkane. Okay, so Sn1 mechanism, as usual, I would use a tertiary. Okay, so Sn1 involves a tertiary halogenoalkane. There is no specifics, so I'm just going to use bromoalkane. I hope you can see. So Sn1, the number 1 means there's only one species involved in the first step or in the slow step. So that means your nucleophile will attack later. Don't forget the polarity of your carbon halogen bond. Since bromine has a higher electronegativity value, the carbon-bromine bond will break and the electrons will be given to bromine to form a bromide ion with the lone pair of electrons. That means we form a carbocation intermediate with a positive charge on the carbon because it has lost the electrons in the bond, and then comes in your nucleophile, which is a water molecule, and the lone pair is on the oxygen. We only need one lone pair, okay? So the lone pair will be donated or given, shared with the positive carbon on the carbocation to form a new carbon-oxygen bond. Now, please take note that oxygen has given its electrons, so oxygen will develop a positive charge. And also you notice that there are 3 bonds around this oxygen, okay? Next, in order to remove that positive charge, one of the oxygen-hydrogen bond breaks and the electrons in the bond will be donated to the oxygen to leave you with an alcohol. OH, and then there's a lone pair there, okay? So your hydrogen, because it didn't get the electrons, it becomes H plus, H plus, and the other product is your bromide ion. So you form a HBr. Okay, so this is the mechanism of Sn1, which is pretty similar to the mechanism of ammonia, except this time the lone pair is sitting on the oxygen, whereas in ammonia, the lone pair is sitting on the nitrogen. The most important thing that students always forget is that when a neutral nucleophile, a nucleophile that has no charge, donates its lone pair, themselves become a positive species because they are giving away its electrons. Whereas carbon, who is receiving the lone pair of electrons, will be minus. Okay, so plus combined with minus, they cancel out. I don't know why it's stuck. Is it okay? Okay, my screen just froze. Okay, so what I was saying just now, carbon is currently positively charged, but when it receives the lone pair of electrons from oxygen, it becomes negative. So they cancel out, carbon becomes neutral. But oxygen, however, because it forms 3 bonds, it develops a positive charge. In order to cancel out or remove that positive charge, we need to donate a pair of electrons to that oxygen. Okay, please let me know when you're done. Okay, next is the Sn2 mechanism. Sn2 mechanism is usually for primary halogenoalkanes. So I'm just going to use a simple bromoethane, right? And don't forget, make it a habit when you draw the molecule, always draw the dipole straight away, okay? So Sn2 mechanism means there are two species attacking in the first step. Lone pair is important. So the lone pair is attacking the slightly positive carbon, forming a new carbon-oxygen bond. That means the carbon-bromine bond must be broken. That brings us to a transition state. A transition state is where you have 5 bonds around the carbon. One is in the process of making, one is in the process of breaking. So usually this is drawn with a square bracket. At the moment, it's not charged, okay, because our halogenoalkanes is neutral and our water molecule is neutral as well. So you don't have to do anything in this stage. And then automatically the carbon-bromine bond will just break. The bromine leaves as a bromide ion. Carbon-oxygen bond is newly formed. And please take note that this oxygen forms 3 bonds. So it has a positive charge. Your bromide becomes Br minus. Hazwan, what happened to you? You just joined. Oh, he's not joined yet. Okay, the next step. Hazwan, what happened to you? You just joined. We're almost done anyway. Okay, so there's a positive charge on that oxygen. In order to remove that positive charge, the oxygen-hydrogen bond has to be broken. The pair of electrons will be given to oxygen to cancel out the positive charge to give you the final product, that is the alcohol, which is your ethanol. You can choose to draw the lone pair on the oxygen, or you can just leave it as it is, OH, right? So that means your other product would be H plus from the water, Br minus from the halogenoalkanes, okay? So it is important for you to show how you have lost that hydrogen. You don't just simply, you started with 2 hydrogen attached to oxygen, and then you end up with 1 hydrogen. If they require you to draw the mechanism, you have to show the steps. You cannot just skip it, okay? Please let me know when you're done. Okay, good. So what I want you to focus on is that at the end of the reaction, actually at the end of any substitution reaction, but this time we're talking about hydrolysis, you notice that there is the halide ion, whether it's bromide, chloride, or iodide, okay? Whether it's Sn1 or Sn2, you will always have that halide ion at the end. Okay, so what is the implication of this is when you use silver nitrate, aqueous, okay, the aqueous will first hydrolyze your halogenoalkanes, and then your silver ions will combine with the halide ions. If you remember, the tests for halides under your qualitative analysis notes, you will use a silver ions. Okay, so because silver ions produce precipitate with either chloride, bromide, and iodide at different and producing different colored precipitate as well. So we can use this as a test. We can also use this to study the rates of hydrolysis. How fast is the precipitate being formed? How slow is the precipitate being formed? And then in terms of color, if it's a white precipitate, that means it's silver chloride. Chloride must be present in this reaction. Okay, if it's a cream precipitate, that means it's a silver bromide precipitate. Bromine or bromide must have been present in this reaction mixture. Okay, so this is all useful for if you do not know the halogenoalkanes. Okay, of course, if you already know the halogenoalkanes, then there's no use for you to do a test to it. Okay, testing is usually done for a compound or a molecule that is unknown. We do not know what's inside. Okay, we do not know what it contains. So you should already know by now that when silver combines with chloride ion, it produces white precipitate, and that white precipitate is your silver chloride. When silver ion combines with bromide, you get a cream precipitate, and that cream precipitate is a silver bromide. And when your iodide combine with your silver ions to produce a yellow precipitate, then that's your silver iodide. Okay, so this is why we use silver nitrate. Use one reagent can do two reactions. First, it hydrolyzes the halogenoalkane. It breaks the carbon-halogen bond. That's what the water is for, the supply of your nucleophile. And then the silver ion is a convenient ion used to test your halides or halogens. Okay, so the halogenoalkanes have different rates of hydrolysis. So this reaction can be used as a test to identify halogens in a halogenoalkane. Okay, I think this is not in your notes, so you can copy this down. Reacting halogenoalkanes with aqueous silver nitrate solution will result in the formation of a precipitate. Okay, so that second point is that the first one is not. So please copy down the first one. Please let me know when you're done. After you're done copying that, I would want to go back to page 2 of your notes because I skipped something from page 2 of your notes. So I would like you to copy point number 1. The halogenoalkanes have different rates of hydrolysis, so this reaction can be used as a test to identify halogens in a halogenoalkane. So why do they have different rates of hydrolysis? Okay, so this all depends on the bond energy, which we looked at on page 2 last time. Okay, right, going to page 2. Oops. So we've already seen last time that carbon fluorine has the strongest or the highest bond energy. That means it's the most difficult bond to be broken. Carbon iodine is the weakest bond. That means it's the fastest or the easiest to be broken. So hydrolysis depends on this idea, this theory. Obviously, the one that is easier to be broken will be the fastest. Okay, and good thing is that we can use silver nitrate to investigate this reaction, to time the reaction. So whenever we have a reaction that we can observe, that we can see, we actually can investigate it. Okay, for example, like the formation of precipitate. You've done this reaction in class where you put a beaker on top of a paper that has got writing on it, and you record the time taken for the precipitate to fully cover the text or fully cover the paper below. Okay, so you can always record the time taken for the precipitate to be formed or to be opaque. Okay, so this is the idea of using aqueous silver nitrate, because when we react halogenoalkanes with aqueous silver nitrate solution, it will result in the formation of precipitate. Now, that formation of the precipitate is actually the second part of the reaction. The first part is that your halogenoalkanes must be hydrolyzed first. If you don't release the halides into the solution, that it wouldn't produce a precipitate. Okay, so if you didn't have water, if you just use silver nitrate molten, there wouldn't be a hydrolysis reaction and you wouldn't be able to form a precipitate with your halides. Okay. The rate of formation of these precipitates can also be used to determine the reactivity of the halogenoalkanes and to identify the halogen in halogenoalkanes. Okay, so I will just write down the equation of what's happening here. First reaction is the hydrolysis of halogenoalkanes with water. I've got about 6 minutes. Can I do this? Yes, I probably can do this. So I'm just going to use iodoethane, but you know that this works with bromoethane, chloroethane, maybe not so much with fluoroethane because the carbon fluorine bond is strong. So in this reaction, the carbon iodine bond is being broken using water. Plus H2O. And this H2O comes from the aqueous part of AgNO3. Okay, so hydrolysis is happening. We form an alcohol, which is not our concern for this reaction. The one that we're interested in is really your iodide ion plus I minus plus H plus. Okay, the second reaction is what we call the precipitation reaction, where your iodide ion will react with Ag plus from silver nitrate. Okay, iodide ion is from the hydrolysis, product of hydrolysis. okay, to form a precipitate silver nitrate solution, okay? Please take note of the state symbols. Iodide ions is aqueous, silver ion is aqueous, and then you form a silver iodide, which is a solid, which is a precipitate, and therefore is a solid. Okay, so this is where we see precipitate form. So this works with other types of halogenoalkanes as well. So you just imagine if you change the iodine with bromine, the carbon-bromine bond will break. You would produce bromide ion. The bromide ion will react with the silver ions from the silver nitrate, and you will form silver bromide, which is cream in color. Okay, so that's the a nice way of testing what's inside your halogenoalkane, what halogen is present in your halogenoalkane. So it's a 2-in-1 reaction. First reaction is the hydrolysis, and second reaction is the precipitation reaction. Okay, and at the bottom of your notes, the fastest nucleophilic substitution reactions will take place with the iodoalkanes, and the slowest nucleophilic substitution reactions will take place with the fluoroalkanes. There's the text that says the rate of the substitution reactions, the rate of hydrolysis actually depends on the strength of your carbon halogen bond. So this first step of the reaction, if this bond is easier to be broken, if this bond is weak, then this reaction is fast. You form precipitate really quick. However, if this carbon halogen bond is strong, it takes longer to break, and the formation of the precipitate will also be slow, and it will take a while. Right? So just make sure that you read everything else that is on that page. Okay. There's also, they also say that, okay, I think everything that I've wanted to mention or everything that I've wanted to emphasize on is already written on that section on page 2. So make sure you read them. Okay, right. Regarding your paper 1 results, your paper 1 scores,